Next speaker is Professor Jeremy Quastel, and he will talk about polynuclear growth and the Toda lattice.
Thanks, Mikiko. And thanks a lot to the organizers. I had intended to be at the conference, and I deeply regret not being able to come. So I'm going to talk about, as it says here, polynuclear growth in the Toda lattice. And so we've seen already a couple of appearances of Toda in different guises in Neil's talk and some earlier talks. And we're going to see a third one here. And I think one of the interesting big questions is, are these appearances even related to each other, or is it just because Toda comes up a lot? So let me start by explaining to you what polynuclear growth is. And I hope people ask questions. I'm not assuming that everybody knows. Okay. So polynuclear growth is a growth model. We've got a height function, which is it's a function on the real line, but mapping into integer values. And just for the sake of simplicity, let's assume momentarily that the function just takes steps up or down by 1 here. So there's a picture of one of these height functions. And these functions are growing in a random way, and they're supposed to be in the KPZ universality class. And so let me tell you the growth rule. So the rule is very simple. You can think of the places where the function goes up as pluses and where the function goes down as minuses. So you can either think of this as these height functions or these pluses and minuses moving on R. Pluses move to the left with speed 1, deterministic. And minuses move to the right with speed 1. And when they meet, they annihilate each other mutually. Just so 1 plus annihilates 1 minus. And so that part of the dynamics is completely deterministic. The stochastic part of the dynamics is that these plus minus pairs are created at rate 2 in space-time. So there's a background space-time Poisson process. And whenever you get to such a space-time point in the position and time, a plus minus is created, and then they just start spreading and doing this deterministic thing at the same time. So I hope this is clear. I described it in terms of the pluses and minuses, but it's exactly the same thing in terms of the height function. And moment's thought will show you that it also doesn't matter too much, that I assume that there's only 1 plus or minus at a certain point at the same time. There could be 1,000 of them at the same point, and they just all do exactly the same thing. But when they meet, only 1 plus annihilates 1 minus. Okay, so I hope the rule is clear. This thing's called PNG. It's one of the most important models in the KPZ universality class. Its friend TASEP is another one of these special solvable models. And basically what we're going to see in the talk is that PNG is a completely integrable system in roughly the same sense as the KPZ fixed point, which we'll also introduce here. In fact, you should think of PNG as almost having all the symmetries and behaviors of the KPZ fixed point, except for the 1, 2, 3 scaling invariance, which we'll describe in a second. Okay, so there's just a couple of points. So this is a Markov process, and its invariant measures are actually very easy to describe. You just do a 2-sided continuous time simple random walk. Simple just means it jumps up and down only 1. It doesn't have to be symmetric. It could have an asymmetry where it jumps up with probability p and down with probability 1 minus p. And those are all still invariant. Those would look like states, which sort of look like this and moved up. So those are the invariant measures. And it also has this special skew time reversal invariance property that, well, looking at this formula, it may be not so easy to tell what it means. It says that, so HTX semicolon G just means the height function at position X and time T, where the initial condition was G. And if you want to know if that's less than or equal to some function minus F, and that means less than or equal to for every X, then that's the same thing as just starting with f and running the same thing and asking if it's less than or equal to minus g. And you can just think of this as saying that the process running backwards in time is the same thing as the process just flipped on its head, upside down. Okay. Okay, so that's the skew time reversal invariance, which seems to be connected to solvability in some sense. Okay, so now let's look at some special cases. Very special case is this narrow wedge initial condition, which is basically the case that has been studied before. It's also true that the flat case has been studied before. So those are the two cases known. So this narrow wedge is very, very important in the history of KPZ. Narrow wedge here means that there's initially an infinite number of pluses just to the left of the origin and an infinite number of minuses just to the right of the origin. Or in terms of the height function is 0 at the origin and minus infinity everywhere else. As I wrote on the first slide, minus infinity is allowed in these height functions. Infinity is not allowed, but minus infinity is allowed. Okay, so if you imagine these infinite number of pluses and minuses just spread at rate 1, and any nucleation event which occurs outside of this expanding cone from 0 is just wasted because it hits down to minus infinity. So all the action is in this light cone here. And the blue dots are the nucleation events. And from the nucleation events where a plus and minus are created, we can just follow these lines. These lines here are just the behaviors. Sorry, we're just, oh, and that strangely doesn't work now. Okay. This is where the plus and minuses went from that nucleation event here. And then they meet another, here there's a plus going here, and they meet and they annihilate each other. Okay, so that's just a picture of what's going on. And okay, and so that's what the narrow wedge looks like. It's also true, and this is also something you just have to think about for a second, that the process has the max property in the sense that if you start with the maximum of 2 initial data and then watch their evolutions up to time t, if you started with the max of the 2, then what you see at time t is just the max of the 2 results at time t. And that tells you that everything can be decomposed into these elementary states, starting with these narrow wedges. And so the height function starting from any h naught is actually just the supremum over all y of starting from a narrow wedge at y plus the initial height functions. Okay, so that variational formula turns out to be useful for a lot of things. Okay, so this is the narrow wedges, and the narrow wedges have a illustrious history because the narrow wedge solution is actually equivalent to a Poissonization of the famous problem of the longest increasing subsequence of a random permutation. And that's just because if you have a bunch of points in a box, which I just drew here sideways, that little bunch of points determines a permutation by just looking at how the points are ordered in this eta direction and how that transforms into the order in the zeta direction. So that's just a permutation of however many points there are in the box, which here is n, which is a Poisson of parameter 2t squared, because we've gone up to time t, and so there's t squared here, and the Poisson rate is 2. Okay, and the height at t0 turns out to be nothing but the length of the longest increasing subsequence of this permutation. So this equivalence is what led, in some sense, to the first famous results about KPZ universality, which is because the 1-point distribution FRTX here, which is just the probability that this height is less than or equal to r at some point tx had been shown to be given by a r by r determinant by Gessel around 1990. It's a r by r determinant full of Bessel functions. This formula and its asymptotic analysis allowed Weich and Johansson to prove the corrections to Ulam's problem was just to figure out this 2 here, that what's the average rate of growth of the longest increasing subsequence, but the corrections, which are the really interesting thing, were worked out by Weich and Johansson based on this, based on the toplet structure of this Gessel determinant. Okay. Now, leading up to the kind of thing I want to show, if you define this object alpha sub r squared, which is 1 minus f of r plus 1, f of r minus 1 over f r squared, and those are the 1-point distributions. So these alphas were known in this special narrow wedge case to satisfy some equations, some sort of well-known integrable equations. One is discovered by Borden and then later found out that it had been discovered before in the physics literature, is the discrete Painlevé-2 equation. So this is a famous completely integrable discretization of Painlevé-2. And the other is this Ablouet's lattice, another famous integrable system. Okay. So that's all leading up to our result, which I'll state now. And the main point about our result is that it's a fact which is similar but not equivalent to either of these things, either of this discrete Painlevé-2 or Ablouet's lattice, but also it's true for any initial data. Okay, so the statement is for any initial data of P and G, the 1-point distributions FR satisfy the 2D Toda equation, which I've written here, with appropriate boundary conditions. So maybe I won't talk too much about the boundary conditions, except to note the obvious thing in the last line, which is that the deterministic part of the dynamics takes your initial function. So forgetting about all the creations, it takes your initial function into the soup over an interval of the initial function, clearly. And so for r less than that soup, it's clear that this 1-point distribution has to be 0. So that's a boundary condition, and that actually has to be supplemented by some boundary conditions when r is exactly equal to this soup, which are a little bit complicated to state, so I won't worry about it. But within the region r greater than this soup, everywhere it satisfies this 2D total lattice. Okay, so that's the main result. There's a little, oh, and you may please ask questions if you aren't clear about something. You may wonder what this has to do with the total lattice, unless you're an expert. If for example, you started with flat initial data, then there would be no dependence on x because everything is homogeneous in space. And this thing would reduce to the 1D total lattice by taking the difference of the logs at 2 points would satisfy the standard total lattice q double dot equals e to the exponentials of q. Okay, so that's the relation with the standard total lattice. Actually, a somewhat related result appeared just recently. Let me just mention that by Cafazzo and Ruzza, who considered a positive temperature deformation of the Bessel kernel, which is what's something like something related to what's above, and found out that it also satisfies the 2D Toda equation. But that's more a deformation of the narrow wedge case, whereas we're looking at general initial data. The other thing I want to point out is that the dt squared minus dx squared the sort of nice way to think about it is in these eta zeta coordinates. And in the eta zeta coordinates, it's just d zeta d eta. Okay, so this is the way I want to think about the 2D Toda equation. Is d zeta d eta of log f equals that. That's just a discrete Laplacian of log. So that's the story about the one-dimensional distributions of the polynuclear growth model. And now we're going to go to the multidimensional distributions. Okay, so the so the multidimensional distributions. Now here we have to only look at fixed time. So we still don't know how to study multi-times, though there are some results coming out in the narrow wedge case by Johansson and Rachman, who have some related results for multi-time. Okay, so we fixed a time, and now we look at n positions in space and ask what the height function looks like at those positions. And the important thing is that once one has this information, these are the finite dimensional distributions which determine the total distribution of HTX, just like the finite dimensional distributions of Brownian motion determine its total distribution. So these are actually the transition probabilities of the PNG. So these things just define the transitions probabilities of the polynuclear growth model. And so if you have these things, essentially the polynuclear growth model is solved. Okay, so we'll introduce a variable x, which is just the sum of the xi's. And r, so r here is going to go up and down by 1, but by 1 in each coordinate. So r plus 1 means you add 1 to every single coordinate of the r's. And r minus 1 means you subtract 1 from every single coordinate of the r's. And what the thing tells you is if you look at f of r plus 1 over f of r, then that's actually can be computed as an n by n determinant. So here n is the size of the finite dimensional distribution you're looking at, of a matrix QR, which I'll tell you what it is later. But the main point is that this QR actually solves this non-Abelian 2D Toda, which we actually saw, I think, in Neil's talk already. And the equation, well, the equation is there. I think the experts may see something in it, but otherwise you just know that there's some completely integrable equation which is being satisfied by these matrices Q, and you take the determinants, and that gives you the differences of the F's. And so in a sense, the whole problem is solved. Okay, so the as I said, the narrow wedge case, one knows what the F's are, and in the and Praher and Spahn actually use that to take a limit and get the Airy 2 process. And in the flat case, these finite dimensional distributions were also known, but not this, maybe in the stationary case it was also known. We're only doing deterministic initial data here, but the initial data is arbitrary. Is there a question?
Yes, just a quick question.
Yeah.
So this is John Harnett.
Yeah, hi.
Hi. So, okay, if one didn't do the two-dimensional, just the one-dimensional, presumably this has a lax representation, which is just exactly a block diagonal version. I mean, block triangular version of the usual scalar one.
Yes, and I hesitate to write it, but that's exactly right. It's in a famous paper of Takazaki and Ueno, which you can look for it there. I can show you exactly where it is, and it's exactly what you just said.
Okay, thanks.
It's just a little complicated to write. Are there any other questions? Okay. So the main point is that the finite dimensional distributions of this thing are satisfying these completely integrable. Now relate this to similar things which we discovered in the last couple of years about the KPZ fixed point. So the KPZ fixed point is a scaling invariant Markov process, which is expected to be the universal limit of all models in the KPZ universality class under this 1, 2, 3 scaling of height versus space versus time. And these scalings are actually written here in the middle. And so any model in the KPZ class is supposed to converge to this KPZ fixed point under that 1, 2, 3 scaling, or if you like, that's the definition of the KPZ fixed point. As I said, the scaling is here. So the definition is that a model is in the KPZ universality class if it has a height function or maybe a free energy, which looks the same as a height function. And under this scaling with appropriate constants, it converges to this special model, the KPZ fixed point. So the KPZ fixed point has analogs of all the things I just said. There's a equation for the 1-point distributions, which is just the KP equation. So the 1-point distributions, so little q here is the derivative in R of the log of the 1-point distributions, and it's supposed to satisfy this equation, which is KP. For the multi-dimensional distributions, they're given by the traces of a matrix. So the determinant has become a trace of a matrix Q, and it and its derivative there, little q is just the R derivative of Q, satisfy a matrix version of the KP equation, which is this one here. Okay, so these again are all well-known completely integrable systems, this matrix KP. And of course, one can wonder if under this KPZ scaling, the Toda and the non-Abelian Toda converge to these KP and matrix KP. Strangely, although that's supposed to be a folk theorem in the literature, if you look in the literature, the actual consensus is that it's false. And the idea behind it being false is that these equations, these KdV, KP equations, are first order in time, whereas the 2D Toda is obviously not first order in time. Of course, I ruined this by writing it as d zeta d eta, but okay, that's not first order. But remember, that's dt squared minus dx squared. But that's just because they didn't get the scaling right. This scaling is a little bit hard to see. And once you put in the 1, 2, 3 scaling and define appropriately your rescaled distribution functions, you could actually just check directly, not rigorously, because you don't know that these equations are well posed. So that's a side issue. We haven't yet proved everything's well posed. But at a formal level of expansions, you definitely get that the 2D Toda converges to the KP equation, and the non-Abelian 2D Toda converges to the matrix KP equation under this these complicated 1, 2, 3 scalings. It's very hard to see. If you expand f epsilon, then you get equations at the order of epsilon 1/2, epsilon to the 3/2. These things turn out to be 0 up to the 4th order in epsilon to the 1/2, and at the 5th order one sees the KP equations, and similarly for the matrix version. Yeah,
I just put it in my. Right. So probably this has nothing to do with it, but besides the KP equation and and Toda equation, there's also the whole KP hierarchy, which involves an infinity of
yeah.
But what's well known is there's also a 2D Toda hierarchy. And of course, just from the construction, if you freeze 1/2, I mean, you have twice the number of variables. If you freeze any, either the right-hand variables or the left-hand variables in the 2D Toda, that definitely gives you a KP tau function. that
Oh, yeah,
for
right.
each site, for each lattice site.
Fair enough, but this is a really interesting question, and I don't know the answer, and I have no idea how to see any of the other equations in the hierarchy from these growth models. If you have an idea, I'd love to know. I don't know what they would be.
Okay.
I mean, of course, you can sort of define them artificially, but as a sort of physical object in the from the growth models, I don't see them. Yeah. So just going on, the variational principle is just recreated at the KBZ fixed point level. It's just it's written exactly the same. It has a sort of slightly different meaning, but that's just because we're solving the KBZ fixed point instead of the KBZ equation. In fact, if you wanted to prove rigorously that the PNG goes to the KBZ fixed point, it's sort of implicitly proved in a paper of Duvrin and Virag, which unfortunately got hidden here. They have a method to sort of prove these variational formulas converge to the limiting variational formula for a bunch of other models, and it'll actually work for this model. So as long as H0s are compactly supported, that just means they're minus infinity outside of some finite box, then this is proved. So our goal here isn't exactly to prove that PNG goes to the KBZ fixed point, but to find the integrable structure of the KBZ fixed point in a microscopic model. Okay, the Q which I described before is actually the resolvent at the origin of a operator KPNG whose Fredholm determinant is giving you these distribution functions, and I'm going to talk about that in a second. One point I want to make is that the some people may have heard me say this before, but the Tracy-Whittem distributions, which are just appearing as the one-point distributions of the KPZ fixed point, starting from the narrow wedge or the flat initial data, are now seen to be nothing but special self-similar solutions of the KP equation. In fact, you can just write down what the self-similarity should be just from basic principles for starting from a narrow wedge or starting from flat. And then the KP just reduces to ODEs, which are clearly equivalent to the Pan-Levade 2 representations of the Tracy-Whittem distributions. So that's all they are. They're just special solutions of KP. So now I want to just talk about this Fredholm determinant representation. So all the results above here, these formulas, the fact that these things are solutions of these integrable equations, all is derived directly from this from these determinantal formulas for the finite dimensional distribution. So I want to show you this determinantal formula. Okay, and then there's an analogous determinantal formula for the KPZ fixed point. It's just a little bit easier to describe actually in the case of the PNG. Okay, so here come the formulas. It's a little bit shocking at first, but I'll describe everything here. Okay, so as I said before, the finite dimensional distributions are just given by a Fredholm determinant of an operator KPNG. And so what happens is that you give you start with your initial data H0, and out of that H0 you produce an operator which is depending on these extra parameters T and X1 through Xn and R1 through Rn. And the Fredholm determinant then gives you these finite dimensional. Okay, so how does this work? Well, so here's the operator is acting on a n-fold product of L2 of the positive integers. And so it's an n by n matrix. And so I'm showing you the ijth entry of that n by n matrix here. That's called Kij. And the first thing to see is how this depends on the r's and the x's and the t's. And what I'm claiming is that it's essentially trivial. So how it depends on the r's is just conjugations by this shift operator, tau. So tau is just the shift operator. So it sort of shifts by minus rj on the right and by rj on the left. So it's just a conjugation by the shifts operators. All these operations that I'm doing now are not occurring on L2 of z of the positive integers, but on all of L2. So I'm going to think of Kij as an operator made out of pieces on all of L2, and then restrict it to L2 of z positive. Okay.
So the determinant would not change if you remove the taus.
No, that's the whole point. It will change.
But you said it's conjugation.
Because the taus are acting on the full L2 on L2 of z. Every action on here is on L2 of z. I was just making that point because it's a little confusing in this formula in this formula. But then you calculate the determinant on L2 of z positive. So you can't just unconjugate on L2 of z positive because they're acting on the full L2. Everything's acting on the full L2. So it's just a bunch of conjugations on the full L2. And actually, you can see what happens in X. In X, it's just a conjugation by these by e to the xj of this discrete Laplacian. So you see you have e to the xj of discrete Laplacian, and then e to the minus xj of discrete Laplacian. Okay. So these things all turn out to make perfect sense, and you can conjugate by those on the full L2, but you can't, as I'm just saying, deconjugate once you go to the L2 of z positive. Okay, and that's what makes the non-triviality here. And then in T, you see it's just a conjugation by e to the t of this 2 times the balanced gradient operator. There's the balanced gradient. Okay, and the discrete Laplacian is just the standard discrete Laplacian. So the main point is that there's sort of a base operator, which I'm calling this curly T here. Once you have that base operator, the whole thing is just how to get your K, depending on T's and the X's and the R's, is completely trivial. It's just conjugations by these operators, or you can think of it as a linear flow upstairs in operator land to get from T equals 0 to the T's and the X's and the R's. This base operator T. This operator is you give it the H0, and you have to produce this operator, and you do it by what we call the scattering theory. And what you're scattering off the H0 in order to probe the H0 is the invariant measure. So for the KBZ fixed point, the invariant measure is Brownian motion. So you scatter off your initial height function with Brownian motions. Here, the invariant measure is these simple random walk paths. And it actually doesn't matter which invariant measure you choose. So we'll just choose the balanced one. So that's the symmetric simple random walk in continuous time. And so the way you create it, except for these little conjugations by these discrete Laplacians again, is through a hit operator. So what you do is you just ask, if I have a continuous time simple symmetric random walk going from u at time A to v at time B. So there it is, u at time A to v at time B. That's expectation is just the expectation over the simple random walk bridge from u at time A to v at time B of this phi of g is the simple random walk path. This is a simple random walk. Minus your initial data. And all that does is ask you, what did you cross your initial data? Did you actually ever meet it? So the hit operator just asks you, what's the probability for a symmetric simple random walk path from A to B, starting at U and going to V, to actually have crossed below the initial data H, entered its hypograph. Okay, so that's how you create this operator P hit. And you use that as the kernel of the sort of base operator, which you then conjugate to get the k's. And then you take the Fredholm determinant, and that produces your finite dimensional distributions of the PNG. Okay, so that's the scheme. And at the KBZ fixed point level, everything is exactly the same, except that simple random walk paths have been replaced by Brownian motions, and the discrete Laplacian has been replaced by the Laplacian, and then this balanced discrete difference operator. Well, what happens is that thing under the KPZ scaling actually goes to the d cubed operator, the area operator. And so if you just replace upstairs the grads by d cubes and the Laplacians by Laplacians and the hit by a Brownian motion, this is the formula for the KPZ fixed point. So you see it's just PNG is just really the exact discrete version of the KPZ fixed point. Okay, so you've got a kernel K, depending on all these parameters. Well, it's a kernel. These are the kernel variables U and V, but it also depends on your time and your x's and your r's and your initial function h, and because it depends on so many parameters and satisfies so many equations and all these parameters, this is how you get these Toda equations to come out. So the Toda equations actually come from the fact that d eta and d zeta. Remember what d eta and d zeta are? They're just dt plus dx and dt minus dx. And dx means dx1 plus dx2 plus dxn. So here you can see these two equations, which you can just check, hold for this k. And a huge algebraic machine tells you that actually means that they satisfy these Toda equations. Okay. So that's where the Toda comes from these equations. From these linear equations for k become the Toda equation. And then you can also wonder why on earth it is that these determinant of I minus k would actually give you the transition probabilities. Well, that could only be true if these Fredholm determinants actually satisfied the Kolmogorov backward equation for the Markov process. Well, that's because in H and T, they actually satisfy this equation dtk equals all k, which looks awfully lot like the Kolmogorov backward equation itself. But actually, we wanted the Kolmogorov backward equation for the determinant. But as it turns out, if you take the derivative of a determinant, you just get the determinant times the trace of I minus k inverse times the derivative. Now, if you do that with L, because L is not a differential operator. Well, L has two pieces. It has a deterministic part, which is like a differential operator. So that part you would believe that this is true. But it also has a discrete part, which is not like that. But it turns out that discrete part actually produces a rank 1 in the LK, and therefore this is also true there. So the fact that the determinants are solutions of the Kolmogorov backward equation is just the fact that the K's actually satisfy the Kolmogorov backward equation. And the fact that the K's satisfy the Kolmogorov backward equation is what I want to end the thing with. This is actually a really new thing that we learned with PNG. You can't see this in any model before this. You have something similar in TASEP, which you can actually check without any understanding. And at the level of the KPZ fixed point, well, maybe something like that is true, but we have no idea what the generator of the KPZ fixed point is. So you can't, I mean, you can check it formally, but the generator doesn't make any sense. Oh, and I just want to mention that these forms of these, the form of the K actually goes back to bi-orthogonalization problems for TASEP, which were known already about 15 years ago by Borden, Ferrari, Prahofer, and Sasimoto. So they had, this form is actually taken from there, though it's not explicit in any of their papers. But once you look at their papers, you can actually see that such a form must be the general thing. Okay. And yeah, before I go into why DTK is LK, I just want to point out that this is what we mean by complete integrability. That if we want to actually solve the PNG problem, and solve the PNG problem means to go to actually compute the Markov transition probabilities. So usually you can't do that for a Markov process, but here you can actually solve the entire family of Markov transition probabilities. And you do it by, you take your H0 and you scatter by the invariant measure to produce these operators K, and up in operator land to go from your K to your K at time T, and looking at the X's and the R's, which I call A here, is just completely linear, as I pointed out before. It's a trivial evolution. And then your Fredholm determinant pulls you down to the transition probability. So it's just exactly a kind of infinite dimensional analog of the way you solve KDV or KP. Okay, and yeah, just to mention this key point for us is why the K's actually satisfy this Kolmogorov backward equation. And this is actually a very, very simple fact. So the fact is here. Before that, I just checked that it has the right initial data, but I'll skip that because we're a little bit short on time and I think people want to go have dinner. So the main point is that if we apply the generator in H onto these hit probabilities, well, the generator just means to do this. So this is just the definition of the generator. You run H forward in time to get HT, and then you evaluate the thing and divide by, look at the difference from time 0 and take the limit as t goes to 0 divided by t. But because of skew time reversal invariance, instead of going forward to time t, I can just think of taking the G. Now remember what the G is. G is just a simple random walk path going from U to V, from time A to time B. But I can take the G and I can run that thing backwards in time instead. A little bit tricky. I should make it minus, sorry, I should, because it's minus the height functions, I should make it plus infinity everywhere else and then run it backwards in time. But anyway, you run that backwards in time, and then that's the same thing. But now that I've run that backwards in time, I can actually think of this as the reversed generator acting on the G's. But now the reverse generator is inside the expectation. It's expectations over the invariant measure, of L star, but L star is just the thing backwards in time, which is just the thing upside down. It has exactly the same invariant measure. So expectation over the invariant measure of the generator acting on a function should be 0. But here it's not exactly the invariant measure. It's the invariant measure conditioned to go from U at time A to V at time B. So you're not going to get 0. You're going to get some funny boundary terms when you try to integrate out the L star. So you actually do this calculation. This is a slightly difficult calculation, but you can actually check that those boundary terms are exactly the commutator with the gradient operator. But when you differentiate in T, you just pull down the commutator with the gradient. And that's why DTK is LK. So that's the mechanism why these things satisfy the Kolmogorov equation. And I'll stop there for questions.
Yeah.
Jimmy, could you go back to the slide with the Kolmogorov backward equation?
This one?
Yeah.
Yeah, okay.
So, okay, so these are integral operators. And I guess the L...
Integral operators, yeah, sure.
It's not the kernel, it's the operator.
Yeah.
And L, I guess, plays the role of the Markov matrix or something like that.
L is exactly the Markov matrix, if I understand you correctly.
Yeah.
We call it the Markov generator. Yeah.
Okay, so somehow sums are replaced by integrals, but somehow the sum of the I guess the rows must be 0 or something like that, or the column. I'm not sure.
On which one? On the K?
On the L.
On the L, yes, I guess so.
So there's some kind of integral that must be 0. I don't know what the sum of what it means to take the sum of the row elements for an operator, but there must be some kind of probability conservation type of condition.
on the K.
Right, that's for the
Yeah.
K. But the
Yeah,
infinitesimal one.
except that the K's are nothing like probabilities anymore. They've been all messed up. They're, I mean, if you look at the K upstairs, it's not a probability anymore. It's a crazy thing. You see, even here, some of these e to the x Laplacians have been taken like backwards heat equations. Of course, they're discrete, so it all makes sense. But K is a wild object. It's not positive in any sense.
Is there some sense? Oh, it's not. So there's no sense in which you can say that the sum of the, I don't know if it's the rows or the columns for the forward and the backward, but that's equal to 1, and for L it's equal to 0.
Maybe, maybe I hadn't thought of that. I mean, my impression was the K was way too wild to think of questions like that. But for L, it's fine. I mean, L is a very explicit thing, right? I mean, L is just the generator of pluses moving to the right at rate 1, which is just a derivative, and minuses moving to the other way around. Minuses moving to the right at rate 1, and pluses moving to the left at rate 1, and then you have this creation operators. And it's a very explicit thing. I just didn't want to write it because it takes a few lines to write. But it's a simple operator, just some derivatives and plus some annihilations plus some creations.
So does it satisfy the Markov condition?
Which one? The L?
Yeah.
Oh, of course. Yeah, it's a Markov generator. It definitely satisfies that. No question. Yeah.
Okay.
Yeah. You just mean that, L of 1 is 0.
Yeah,
Sure. No problem.
Yes, that's right. That's what I meant.
Yeah. In fact, if you look at L, I don't want to write out L because it's a little bit annoying. It takes a few lines. But if you look at it, the fact that L1 is 0 is complete triviality.
Maybe I want to ask 2 questions. So one is about the scattering by invariant measures, and you said, I think invariant measures can be anything, or so the
invariant measure. Oh, what I meant was, so the invariant measures are continuous time simple random walks. Okay. They don't have to be symmetric. Okay. It could want to jump up more than it jumps down.
So it does not depend on this scattering.
No, in fact, if you check, you can check that if I didn't use the symmetric version in the construction of the P's or the T's or the K, then so I used another version, then what you'll just get is a conjugation of the K by something which a conjugation of the K by multiplication operators, which is allowed to deconjugate under L2 of Z positive. So it doesn't matter. So the determinant turns out to be the same.
So if more generally, if we have many big family of invariant measures, then maybe we can use any.
You can use any one. And what happens is that in these problems, you definitely want to use the convenient one, and otherwise the thing looks very ugly and you don't quite know what you're doing. Yeah. That's right.
Okay, thank you. And the second question is, I think you said Tracy Vedam GUE or E are just some special similar solution of KP. So then I think it's related to the Professor O'Connell's talk. He said after it's a discussion time, there should be Tracy Vedam matrix version, and that this matrix KP's special self-similar solution.
Yeah, it's a good question. I think you have to ask Neil if that's what he meant. But I didn't get the impression he meant that, but it could be he did, and I just didn't understand. I don't know what's the relation between his quantum Toda and our Toda. They're for completely different observables. And you see, it could well be that they're just because Toda comes up a lot in these integrable things.
But matrix KP has some self-similar solution, which is a kind of generalization of Tracy Vedam.
Yeah, that's a good question. I did not. So you don't have the same sort of self-similarity when you start to look at 2-point functions. There's a problem with the matrix KP because in the matrix case, this matrix Q is not as physical an object as it is in the scalar case. So you have to take a trace of this Q to get the distribution function. So I think that it's not even clear. Well, I haven't. It's a good question. Maybe one should try to look for some self-similar solutions of this matrix thing and see if they have some meaning. It's a good point.
Then let's thank speaker again.